welcome to our keynote session. I'm very happy that you're all here. I hope you had a fantastic day at the AI Festival, heard some interesting perspectives. I'm very excited about this perspective. We have Professor Alexander Pretschner from TU Munich here with us. Alexander's accolades are too long to list them all. He is leading the software and systems engineering efforts at TU Munich. He is the founding director of the Bavarian Research Institute for Digital Transformation, and he's also the scientific director of Fortis, that is a research and transfer institute. So given all his experience and accolades and efforts he has done in the community, I'm very excited for him to talk about something that is very dear to my heart as well, namely, will AI replace software engineers? Which I think is an interesting question to begin with, because for the longest times, software engineers have been automating other people's jobs and efforts. Another question is, will they be replaced? So with that, a big round of applause for Alex, and take it away.
I'm going to talk mainly about software engineering, because I think if you want to understand what the impact of generative AI on software engineering is going to be, we need to understand as much about software engineering as about generative AI. And now you know everything about generative AI after these 2 days of your fabulous conference. So I'm going to put more emphasis on software engineering. And in fact, the title in the program was slightly different. The title in the program was "Why Gen AI Won't Replace Software Engineers," or something along those lines. So my first answer to that question is no. And in fact, 2 years ago, I wrote an article for a German newspaper, Frankfurter Allgemeine, where I made the point about why I didn't think that generative AI would replace software engineers. And now 2 years have gone by, and I have needed to adjust my statement with a statement that is the general statement in software engineering, namely, it depends. And this, in fact, is a point that I didn't understand 2 years ago. Software engineering is so diverse that if we want to talk about software engineering and want to argue about the impact of generative AI, we need to understand what the different facets of software engineering are. And this is what I'm going to discuss with you. Now, to start with, you may wonder, hey, isn't this trivial? Of course we're not going to be replaced. The answer is, we will see why that isn't trivial. And in fact, in the newspapers, you see different kinds of arguments. Programmers won't be needed anymore. AI will replace human coders in 10 years. Tech jobs will disappear. And then you have soccer dads who can now write their own apps for their iWatch that they can use to count the goals that their children have scored. And you will realize that these things, in fact, talk about different things because they talk about different kinds of software engineering. And earlier this year, Mark Zuckerberg made that famous statement that I guess everybody has seen: AI will replace mid-level engineers at Meta. Did anybody hear that interview, by the way? It's very much worth listening to, and the reason is that this statement is a statement that he has made, but it's taken out of context, because Zuckerberg, after making that statement, realizes that he has said something outrageous. And you can see that he is pulling back from that statement within that very interview. He's trying to make more relative what he has said. And I'm going to argue why this statement may be right or may be wrong. I can't really judge. But what I'm going to argue is that this statement simply doesn't make sense. Okay, here we are, back again. So I'm going to talk about 3 things. I'm going to talk about software engineers, because we will need to make a set of distinctions here. I'm going to talk about software and software engineering, because we'll also need to understand what software engineering really is about. And then I'm going to argue why I don't think that Gen AI in general will take over, but in certain places, I think it will, and as we are seeing today, it already is. And I'm going to tell you what my main point will be up front so that you can see where I'm moving with the set of arguments that I'm going to provide to you. My argument is that when we develop software, we have an intent as software developers. And an intent is something that is inherently human. A machine does not and cannot have an intent. A human needs to provide that intent. And hopefully software engineers do know what their intent is. But my point is this is an inherently human element that a machine can't take over. And because that is the case, we cannot have a machine develop software. The second part of the argument is, well, maybe we could come up with a formulation of that intent in a prompt. And the answer is, unfortunately, that won't work either, because there's so many decisions to be taken along the development of a piece of software that we can't predict what these decisions may entail and what the criteria will be. And connecting to the last session that we've had today, I think this is also fundamentally related to digital humanism, as at least I see it. When we have software develop code, then we refuse agency and we dodge responsibility. Because if a machine creates the code, who is responsible for that? Which very much aligns with the debate that we've had just an hour ago. So let me start with that idea of software engineers. Now, when people talk about software engineering in that debate, often they talk about coding. And I just want to make sure we are on the same page here. Coding and software engineering is not the same thing. Software engineering encompasses a wide range of activities. I think it's about 20 different activities that most people would agree upon. And while engaging in these activities, they come up with certain artifacts. So, what do software engineers do? They try to understand the needs of users that want to have some system. Then this is written down in user specifications. And there's a difference between needs and requirements. Needs is what is really needed. Requirements is what people think is needed, which usually is not exactly the same thing. Software engineers think about data and model data. Software engineers need to think about a world model. Usually we are interacting with the world and there's some reflection of that world in the software system that we are building. We have an architecture of the different components and data types that we are using. We develop algorithms. We have machine learned models or other kinds of AI components in our system. Oh, and yes, we have code, and yes, we have tests. And we do all these things all the time, and what we teach at universities is precisely these different things, and different software engineers engage in these activities to varying extents, also with changing roles if you consider agile software development. And just this elaboration on what software engineering is shows us that that statement of Mark Zuckerberg can't really make sense. Because what is a mid-level engineer doing? Is a mid-level engineer engaging in activities that relate to needs? Are they engaging in developing algorithms, the world model, and so on? We simply can't say, because it's all these activities. And of course, what Zuckerberg has had in mind is an organizational definition of what a mid-level engineer is. But the first thing that we need to understand is software engineers do totally varying things. So the question is, when we debate the role of Gen AI, we need to consider the role of AI in these different activities, in the creation of these different artifacts. A second distinction that we need to do is different people write different kinds of software. So we have the dad who now can develop an application for their iWatch to count the goals of their children. People who never coded before, they can now code, which is what we call vibe coding, as you may know. That's perfectly fine, but there's nobody to be replaced because these people just didn't code in the past. No problem here. Then, in software engineering, we have a bunch of people who aren't trained professionals, but who somehow ended up in that business because they could make money there. And I phrased that as music teacher turned website developer. These people write comparatively simple programs, And in fact, I think they can indeed be replaced. I don't know if you've ever played with a system like Lovable AI or something. These systems can do pretty good websites, pretty good web applications that are not too complex. And this is, by the way, why my no statement is something that I have adjusted over time. Then we have professionals that are not trained in software engineering, but they do develop software-intensive systems. Think about engineers that build software for cars. They understand the application domain, but they are not formally trained in software. And these people will still need to provide their knowledge of the application domain to the tasks of developing software. And they probably will become better with the software that can be written by AI, but their expertise in terms of the domain is going to be required. And then we have software engineers, professional software engineers with a formal training in there. And I think they as well, for reasons that we're going to discuss today, will be assisted but not replaced. And now we have these different kinds of software engineers. And a second dimension then is they come at different levels of seniority. They can be totally junior or they can be totally senior and everything in between. And I guess this is a figure that most of you have seen. It's from a paper, I think getting back to June this year by Brynjolfsson and colleagues from Stanford. And what you can see here is the development in terms of the number of jobs over time. And the number of jobs here is with respect to software engineering. Where do these numbers come from? From a payroll system in America, 20 million people that are getting their paychecks using these systems. So it's a huge database. And the different lines here, the different colors, correspond to different cohorts, different ages. And what we can see is that the number of software engineers across all classes of age has raised steadily until October 22. Which was the release date of ChatGPT. And then all of a sudden, things break down. What you see here is the cohort of 20 to 25-year-old programmers. What you see here is the cohort of 25 to 30-year-old software engineers, I should say, not cohorts. And what we see here is all more senior people. And for them, well, the job market is developing positively, but slightly less so than before. It's also interesting to note that this doesn't mean it's totally catastrophic because the drop is only 20%. So there are still juniors that are being hired, just in case you are a student, and no worries, just don't belong to these 20% that are not hired anymore. But we can see this kind of relationship. By the way, we can see it in different jobs as well. That's a more general statement. And there's also plenty of things to be criticized with respect to this study, but there is a tendency to see that juniors are not as much hired anymore as they used to be in the past. Good. And now a third dimension is the technology that software engineers are engaged with. They build systems, and one fascinating thing about software is that you can do everything with software. And in fact, we write software for pacemakers, for microphones, for search engines, for AI models. So there's all kinds of systems that we are building. And as it turns out, these kinds of systems, in terms of the application domain, are so different that also the technology that we are using and also the organizational ways of developing software are so different that I would argue we don't really have fundamental laws of software engineering. There's very few statements where most of us would agree, hey, this in general is true. Just very few. And the simple reason is there's totally different kinds of software. A safety-critical car comes with different requirements than a script that I use to scrape the web for getting whatever kind of information. So when we talk about software engineers, once again, we need to think about what is the different set, or what is the set of application domains that we are engaging with. And because they come with different dimensions, there's a lot of things that need to be considered here, such as what is the legacy tech stack, what is the development process that may be prescribed by regulations. There's a whole set of influencing factors that have an impact on the way that we develop software. Now, why am I making that point? Because once again, it simply doesn't make sense to simply say mid-level software engineers will be replaced. That just doesn't make sense because things are too nuanced to be attacked by that kind of blunt statement. And of course, there's good reasons why Mark Zuckerberg did that, no question about that. But for us, we need to understand that this statement is something that no serious person actually can do. That's the first idea that I wanted to discuss with you. My second idea now is going to relate to what really happens when we develop software. I'm now going to abstract from all these considerations. I'm going to talk about what is it that we do when we develop software. And I'm going to come up with a very abstract way of describing what software and software development is that is going to give us the possibility to understand where the human factor necessarily will be. So, just to make sure we're on the same page here, what is software? Software implements functions. What are functions? Functions are mathematical constructs that map input to output. And the idea is that that relationship between input and output is not necessarily described in an operational way. I can say that the square root of some number has the following property: the result multiplied by itself is the original argument that I've provided there. This is a description of what the function is doing. It's a very good description of what the function is doing, but of course, it doesn't tell us how to compute that number. That's a different story, okay? So I have a function, and the function exists independently of its implementation. That's the first thing to be understood. And of course, software is everywhere. You see a few examples here. We have plenty of software in cyber-physical systems, but also in business information systems here. So we have our function. Our function maps input to output, and the way that the relationship between input and output is there for us is jotted down in a specification. And in reality, we often don't have a specification, or we have a vague specification, but people write down roughly what they think the system is going to do. And again, depending on the context, that is more or less precise in terms of what we are doing. And once we have understood what that system is doing, well, we do what engineers have as the only heuristic that has always worked. We do divide et impera. We break the problem down into smaller pieces, try to understand it better, and then solve these smaller problems by iterating on that process. And interestingly, this idea does not just apply to implementing the system, but also to understanding what the system is supposed to do, in terms of understanding what that function really is doing. And we are going to come up with a simple model as to what that really means. And now the idea is the following. When we have understood a function or a part of a function that we want to implement, and again, the point is that that function exists independently of an implementation, then with software, we can come up with an arbitrary number of ways of implementing that functions. The function tells us, hey, this is how the square root, or I want to have a square root function. The square root function is defined as follows. And then I can come up with 20, 50, 70 different ways of implementing that square root function. Computer scientists here in this room will know our pet is sorting algorithms. There's not just one sorting algorithm, there's hundreds of sorting algorithms that all come with different properties here. And now the point is that if we have the problem, so the function that we want to implement, and the set of possible implementations, then somebody needs to decide which of these implementations to pick. And of course, we can pick that implementation at random, but usually we would say, hey, there's some objective that I'm pursuing, and I somehow need to choose the best option for the problem at hand. And usually it's not as simple as that, because the different solutions usually come with diverging qualities. So they may be fast, but eat up a lot of memory. They may be performant, but not secure. So there's trade-offs that we need to decide upon. And who is going to decide upon these trade-offs? There can only be a human, because only the human knows what they want. They have the intent. And we're going to see, and we're going to argue that this is something that an LLM or a generative AI cannot do. In principle, of course, at each moment in time, we could argue, hey, here's a bunch of possibilities, or LLM, please give me a set of possibilities. Here is my specific optimization goal, my goal with respect to the trade-off. Now pick one of those. But this is unrealistic. How do I know? Because we have had agile software development for the last 35 years, which precisely has understood that point that we can't say upfront what we want. I get back to that idea in a second. So the key argument is the following. In a sense, developing software is a decision tree across the different artifacts that we are building. And upon each decision, at each level of the decision tree, somebody needs to take a decision, but taking a decision requires the notion of an intent. And that's the point that I've tried to make in the beginning, I don't think that a machine can have an intent. Why would a machine have an intent? And this, by the way, again, is closely related to the discussion on digital humanism that we are having. Good. Now, how does that work? A bit less vague. When we think about software, then we start thinking about these functions, again, without knowing what the implementation is. So we think about an input domain, input data, and output data, and in the very beginning, we don't really know what's going on there. We just say, hey, I know what the input will be approximately. That's why I've come up with that cloud-shaped figure here. And for the output, that is the same is true, right? So that's the first step. And then when we think about different use cases or user stories, then essentially what we do is we chop that input domain into blocks. We build an equivalence class of inputs, and we say, hey, these inputs somehow relate to the same functionality, and we are going to map those inputs to certain output classes. And maybe we don't really know what exactly an individual input will lead to in terms of an output, but it's just sets, right? So I say, hey, my general use case is I want to do that, and approximately the outcome will be what we are seeing here. So my function that relates input to output now is broken down into sub-functions that map these input domains, these blocks of input domains, to output domains. And as we proceed now, we better understand for each of these user stories how they should be developed. So we now understand, okay, when we think about that user story, there's really those 5 or 7 cases that I'm interested in. So for each of those, I again chop the block of inputs into smaller blocks that pertain to one specific piece of functionality. And I do that for all the input blocks of my user stories. And the same then happens at the output side, and I can continue with that game until after some time I have some mapping of individual inputs to individual outputs in terms of an implementation. And I'm not talking about non-determinism here. Let's just think about it that way. And this, in fact, is what we do when we develop software. We break down functions into smaller parts. And as we do so, we also change the artifact that we are developing, because we go from needs to requirements to specifications and then to code, even though this is totally independent of what the development process really is. And in fact, software has been developed in a variety of ways, as you all know. In the 70s, people have started to think about ways of developing software as a linear sequence of steps, as a linear sequence of refinements. So what I've just shown you is even something that you can, if you want, formalize. Whether or not that makes sense is a different story, but you can at least do that. And this is the time when people came up with the waterfall model, right? It's a linear sequence of steps. In fact, it's not as linear as many people think, but we'll get back to that. And then in the 90s, people realized, oh, wait a minute, that doesn't really work. Because up front, we can't know what our requirements really are, and specifically, we can't know what our requirements will be 2 years from now, or maybe 6 months from now. And that gave rise to that idea of thinking about a development process where the design and the production of the software would be intertwined rather than separated. Because what happened when the waterfall model was developed for software is the following. People were starting to think about how to develop software. Nobody had done that before. So what do you do if you don't know what to do? Well, you ask your friends. Who are the software people friends? The hardware people. How did the hardware people build their systems? They come up with a design and then produced, in fact, mass produced that design. That's what I think the story of the waterfall is. As simple as that. And what agile development did is it undid that separation between design and production. Because it said we can't really do that, we need to intertwine design and production, which then gave rise to a different way of developing software. And in fact, there's something that was published in 1971 by Niklas Wirth from ETH Zurich that is sitting in between. He called that stepwise refinement as well. And that's a different notion of stepwise refinement than Hoare and Dijkstra notions of refinement. And he realized, oh, well, when we develop a system, then there's a bunch of things that we do. What matters now in the first place is, hey, we are going to get back to decisions that were incorrect, that in hindsight have proved to not work, right? So we develop our system and then we realize we got it wrong, therefore we need to go on, which is somehow in contrast with that linear idea. So, the point that I want to make is that if we think about these different artifacts, by the way, these artifacts don't explicitly exist in all development processes. They do not, for instance, exist, or all of them do not exist in agile development processes, for instance, but at least conceptually they exist, and they can all be related by some kind of refinement relation, which I have indicated here by that subset relationship. In that sense of breaking down a function into smaller functions where we have a better understanding of what is going on. And that idea, when you take that to an extreme, as we have seen, is the waterfall model. And just to be fair, the waterfall model was published in 1970. And in that paper, in fact, Royce already had that idea that it's not going to be totally linear, but there will be necessities to get back to what we have done in the last step, or even sometimes across steps. So that is something that people knew. But anyway, the general structure is to get from requirements to specifications to code, which is what the agile world has questioned by saying that is something that can't work, because up front we usually don't know what is going to be done in the next couple of steps. And don't mistake me, I'm a big fan of agile, but I don't think it works in all cases. Depending on regulation, depending on cyber-physical systems influences there, it may not work at all. Also organizational matters are important, but that was essentially the idea. And the crucial insight is that if we think up front about all our requirements and about all the choices that we may want to make in subsequent steps, that is an illusion. We don't know that, we can't know that, and therefore let's just start building a system over time, and as we build it over time, we better understand what we need. So the requirement specification, the intent of what we want to do, co-evolves with the system that is written. And this is in stark contrast with that waterfallish or V-modelish models that we otherwise talk about. It's the co-evolution of specification and system. It's the undoing of the separation between design and production. I think that really is the key behind agile software development. And you're going to see how that matters for our debate in a second. Because now, does anybody recognize that system? Do you know what that is? It's a dictaphone. Okay, in the 2000s, or maybe in the 2010s, people use that to dictate stuff. Who in this room can dictate emails? 1 out of 70. Well, maybe 1/2 doesn't really care. Most of us cannot dictate emails unless they are trivial. And most of you probably are like I am. The backspace key is the most frequently used key on my keyboard. I start writing an email, I start writing a text, and then I delete words and I realize, oh, this is not exactly what I wanted to say. And then I need to reshuffle things. And then I realize that the tonality doesn't really work. And then sometimes I realize I don't really know what I wanted to say from the beginning, so I need to drop the entire email. And what is happening there is that the email is developing as I understand what I want to say. And it's not the case that I can say up front, this is going to be my email, which is something that I could do when writing an email. But I can't do that, which is why I develop my thought as I write it down. It sounds familiar, right? Isn't that very similar to what we have just seen in terms of agile software development? And unfortunately, that idea is great, but it's 220 years old. There's an essay by German writer Heinrich von Kleist about the allmähliche Verfertigung der Gedanken beim Reden, whatever that is in English. What it essentially states is that as we speak, we develop our thoughts. It's a 5-page essay, it's really readable, and it's exactly the point that I'm making here. We develop as we think, and we think as we develop. And if you think about that, this is something that happens all the time. When I'm speaking here with you, I don't know what I'm going to say in 3 minutes. And I don't even know what I'm going to say in 20 seconds. My flow of thought is developing as I speak. I have a friend who is doing clay sculptures. And she tells me it's exactly the same thing with her. When she does one of her clay sculptures, it's not that she knows up front what the final beast will look like, but rather she starts moving things, and as she develops the form of that statue, she realizes what she wants. And I think this is a fundamental design principle. We develop as we think, and we think as we develop. And this is something that is also true for software engineering, and this very idea is what exactly is embodied in the ideas of agile software development. And of course, I'm not saying that that always works and that always should work, that's not the point, but the abstraction is we cannot know upfront what should be developed. Of course, there's people who say, well, it's not a matter of not being able to say what you want, it's a matter of laziness and of hacking just a system, but that's a different debate. That principle that it's at least easier to develop what we want to do is a very powerful element here. And once again, unfortunately, this is also something that Niklas Wirth in his 1971 article had already understood. He also talks about these refinements, and his point is the following: each refinement implies a number of design decisions based upon a set of design criteria. And among these criteria are efficiency, blah, 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 and some others. And students must be taught to be conscious of the involved decisions and to critically examine and to reject solutions. So what does that mean? Within the development of our system, we need to understand in every step what we want, how good the possible solution is, and if it is good enough, we keep it, otherwise we reject what we have done. And now the question, of course, is who takes that decision? And we are in the context here of using generative AI for building software systems. And you may argue, well, maybe that's an LLM, maybe that's a generative AI. And here again, my point is, well, but with respect to which intent? Who is formulating within each of these design steps the intent that would lead to choosing the best design option? It may be the case that if I can write down my intent, that an LLM will come up with a solution, specifically when we think about agentic AI these days, but that doesn't solve the problem of who comes up with the intent. And this is where we need software engineers. And by the way, that applies to 2 dimensions. Software engineering always has a technical part, which is the software domain, if you wish, but software is operating in some application domain, and we have that application domain as well. And now, let me, in fact, finalize my ideas here. So the first ideas, and I'm not sure if everybody is familiar with the way that software or that code can be developed using AI. The idea is the following: you state a specification, you push a button, and you get a result. And of course, that result may be incorrect, and then you need to iterate. And of course, the quality of the result, of the code that is generated, depends on the prompt that you have provided. Who's a computer science person in this room? Some of you, okay. Think about the following problem. Define a soft link as opposed to a hard link for an operating system. And you see that it's tremendously difficult to make very precise the point of what that is. And the idea is somebody needs to specify that prompt. So I think what we are seeing in terms of generative AI is a generative AI will be good at generating code if the prompt is good. But who writes the prompt? It's not the AI. This, once again, is a person that does that. And of course, then, because we have that cyclic way of developing software system, well, this is going to happen in iterations. And I think this also explains why we are seeing this curve here. Again, remember, this curve shows us that juniors are hired less as opposed to more senior people. And my hypothesis is that that can be explained in the framework of what I have discussed with you here, and that is a junior person cannot precisely specify what they want, and a junior person cannot take a decision with respect to a bunch of different design alternatives simply because they haven't learned to take that kind of decisions. And in a sense, an LLM up front is like a junior person. If I see my first semester students, I give them a problem, they come up with one solution. And they don't even consider the possibility that there could be a different solution. But this is what professional software engineers do. They think about a variety of options and then pick the option that in a given context and at a given moment in time comes with the best trade-off. We were joking with Gertie before. Now, of course, the problem is if we don't hire juniors anymore, where do the seniors come from in the future? That's a big problem, of course, but that's a societal problem. Good. Now, two more thoughts that I'd like to share with you, and that is, if the specification is sufficiently precise, you can expect to get sufficiently correct code. But even if your specification is not very precise, you may get crappy code. By the way, also depending on the programming language that you're using, the code may not even compile. We have just done some experience with C++, and the translation of C++ to Rust. The code that you generate in that process by using an LLM doesn't compile in 60% of the cases, doesn't even compile. So it's not as great as we may think. But let's assume that we have a programming language that is sufficiently well represented on the internet, like Python or Java or whatever, and let's assume that we have a problem that is sufficiently precise specified. Even then, we may end up with results that are incorrect, right? And this is what people usually refer to as hallucinations. So what does that mean? Well, trust but verify. Every artifact that is being provided by such a system needs to be verified. And depending on the granularity, sometimes the quality is good, sometimes it's bad. We are running some practical software development activities, and there what we are seeing is that 80% of the tickets that are created, that are either bug fixes or new functionality, can in fact be implemented by an AI, and they can be committed after manual review, which is a lot, right? 80%. But of course, that is also related to the fact that those people who write the tickets know exactly how to write tickets, and they can be clear about what they specify. So the idea is that, in fact, that is an implication for, I think, the way that we are teaching computer science. We will move forward from creating to verifying. I believe that indeed we will come up with engineers that are capable of breaking down a problem into smaller problems, that can precisely specify what is required, and who then can judge what is created. And it may be that it's necessary to learn creating first before we can gain that capability, but I think this is how the workflow of software engineers is probably going to change. It's going to be shifted from creation to verification. Good, and how does that work then? Once again, well, it's working in cycles. You start with a prompt, you get a result, you verify the result, you readjust the prompt, and, well, hopefully you come up with a sub-functionality that after some time resembles what you wanted. And I would argue that during that process, it's not just that you need to verify if the code is correct, but you're also going to understand that the specification, the prompt that you have provided, wasn't really adequate either. And of course, one question is the code correct or adequate that I'm getting? The other question is, hey, what about productivity? What about cost effectiveness? And if you buy that idea that we are going to see a shift from creation to verification, then we don't gain anything if the net effort is still the same. Now remember, nerd fora that I'm consuming 2 years ago, where people said, oh, fabulous, now with LLMs, we used to spend 23 hours on coding and 1 hour on testing, and we're going to replace that by 1 hour of coding and 23 hours of testing. If that is the case, of course, then we don't need to use LLMs. That doesn't make any sense. That's not cost effective. It is cost effective if the overall effort becomes smaller, and in some situations that is the case, in some situations that is not the case. And I'm just talking about effort here. At a more fine-grained level, we would also need to consider different risk classes of the functions that we are implementing. Good. And the state of affairs in terms of understanding productivity when using LLMs is totally unclear at the moment. So what we are seeing is the following. First, there's companies like McKinsey or Boston Consulting. I hope I don't step on anybody's toes here. And they tell us, yes, productivity is going to be tremendously increased. What's the basis for these studies? They ask CEOs if these CEOs think that productivity will be increased. And then they show, oh yes, productivity will be increased. That's problematic, right? People are also doing studies. There's a variety of studies, and there's increasingly more studies of that kind where we do A/B testing. One team uses the LLM, the other team doesn't use the LLM, and we come up with comparable kinds of problems. And what we are seeing there is sometimes the LLM leads to a gain in productivity, and sometimes it doesn't. And the range is enormous. It's in between -20 and 20% usually. And the reason is that, of course, we have different kinds of software problems that we are seeing here. And I think what we need to understand is not if LLMs are better than humans or more productive than humans, but we need to understand where we can increase productivity. And as a side note, what's also interesting is that in software engineering, for the last 20 years, people have argued that the productivity of an individual software engineer is totally irrelevant because what matters is the team. And we have come up with new productivity measures, and all that practical knowledge is now thrown away, swept under the carpet, and we get back to individualized ways of measuring performance. And that's where I would like to stop. So the idea is the following. As we develop software, we necessarily learn over time what we can and what we want to do. And my argument is that up front, I can't say what the decisions are that I'm going to face, and I doubt that we can say up front what our design criteria would be. Everybody who has developed larger software systems knows that sometimes you sacrifice maintainability for performance and sometimes you don't, so there is not the one general rule. The idea is that at every stage of development, we have multiple ways of proceeding. Picking the most adequate option is with respect to an intent. And I'm repeating myself 1,000 times here, that intent is not something that a machine can come up with. And the idea is that if all these solutions are equivalent in a certain way, because we don't really understand what's going on, or in the case of vibe coding, we just don't care what's going on, then indeed it doesn't matter if an LLM creates that code or if a junior developer creates that code. It doesn't matter. What I'm talking about here is professional software engineering. And that again is context specific, of course. Now, my last word here is, please don't mistake me. I've tried to be very nuanced in terms of the statements that I have been making. I didn't mean to say that AI won't help. Quite to the contrary, it will help. What I'm questioning is the idea that a human, specifically a professional software engineer, can be replaced because of that line of arguments that I've provided here. Thank you very much for your attention.
Thank you very much, Professor Pretschner. Okay. I think we have time for a couple of questions, right? Anyone who wants to go first? I have a lot of questions, but I'll keep them to later, potentially. Any questions from the audience?
Or criticism. I'd love to hear your objections, comments, in fact.
I think, okay, yeah, go ahead.
Thank you for the very interesting topic and presentation. I have actually a question about the intent, because I'm not clear about that. Because we see, I'm not a scientist, so nothing to do with that. So what do you mean AI cannot have intent? Because, I mean, if I write an email with Google Gmail, then sometimes it comes, the intended word comes afterwards, before I actually intended actually, so.
Yeah. So in fact, you answered the question yourself, right? You know exactly what an intent is because you realize that the system can guess your intent, right? So what do I mean by the intent? The intent is what I want a system to do at any given stage of development, or what I want to write in a system at any given moment in time. Okay? That's what I mean by the intent. This is where I want to go. The goal, the objective of what I'm doing here. And thanks very much for bringing up that example. What Copilot or Gmail or whatever is doing is they can guess your intent, right? They may say, okay, statistically speaking, when people start a sentence like that, they finish it off by that. And the point is that may reflect your intent, but maybe it doesn't. And I think it's problematic to just assume that you are so statistically normal that what you intend to say is what everybody else in their majority is saying. That's the argument here. And that does mean that sometimes maybe it does guess the intent correctly. What I'm saying is at every moment in time, it's also our responsibility to understand if what is written aligns with what our intent is. And by the way, it's also dangerous. What we know from requirements engineering is if we are given a suggestion of what we think we need, we usually end up with saying, yes, that sounds good to me, even though it's totally not what we have had in mind, which is why we have techniques that we call design thinking, or that come under the umbrella term of design thinking. So the intent is the objective, and the system may guess what your objective is, but having a goal in terms of what you want to do is something that only human can have. Why would a machine have a goal to do something unless we encode that goal as a prompt?
Yeah, I had a similar question about intent, yeah, because your whole argumentation was the intent can't be learned or generated by generative AI. And I don't think this is true, because, I mean, you can train AI to specify the intents, because I'm coming from software engineering. I'm coming from visualization, and we also use the term intent to specify a visualization. And we decompose intent to actions, goals, And if I would formulate better prompts, I could train the generative AI to generate intents.
Yes. And I agree with that point, but what I'm saying is you can't, so at least in software engineering, for your HCI kind of things
Visualization, not HCI.
Visualization, yeah, for that kind of things it may be different. My point is that we cannot say up front for every individual step what the intent would be. And in that sense, I can't train the system. And that is exactly the lesson that we have learned with agile software development. We cannot know, and we do not know upfront where we want to go. And maybe the difference is, once again, the broad range of different kinds of software that we are writing, that we may come up with different decisions that we take as we proceed, and we can only understand what the intent is at a given moment in time if we have enough information. That's my argument.
Okay, but I could learn it.
Yeah.
I could.
Maybe you could learn. Yeah, so
think in the future. Think in the future.
I don't disagree that you could learn the intent, but I doubt that I, as a human, we as software engineers, in the beginning, can say up front, here is a set of intents that universally apply to each development step. That is exactly something that I doubt. Because again, sometimes you take, at least from my software engineering practical experience, you take even conflicting and contradictory decisions. Sometimes you say, okay, now maintainability is important and beauty of the architecture matters. And then sometimes you say, no, I just can't justify that we need to go on.
Thank you.
Lucy was first and then...
Yeah, thank you very much for your talk. So, if the software engineers, which are very experienced, are needed from the industry, one solution may be that we produce software engineers which are very experienced in the university, which is probably almost impossible. But I would like to hear your opinion. Can we change the education in such a way that we have, to the end, these software engineers, very experienced, which are required from the industry?
Yeah. Excellent question. So here's my crystal ball. I'm going to tell you what is going to happen. So I think we cannot do that. And the reason is that when you work on large projects, there's so many influencing factors that nobody can predict. And of course, what we could do is we could say, hey, students, we give you whatever kind of problem, and now develop a system that does this and that. That, of course, is something that we could do, and I guess you do that here as everybody else would. We give them practical projects that are of a moderate size where they learn exactly that kind of things. Now, if we say we want to increase that knowledge, then that means that we need to take away something from our curricula. And I guess, I see Gati as your dean. The most unfruitful discussions in every department meeting that I have been in are around, okay, let's swap the curriculum. Let's take something out and let's move something in. It's an extremely difficult decision. So, if we say, hey, we put students into practical organizations where they develop software and they do that for 2 years, then I need to get rid of a bunch of classes. And I'm not sure what these classes would be. That's the first part. The second part is, my perspective has always been they learn that soon enough, they being the students. If they just go on the job, they do that. I'm not sure this is something that we need to teach them in the beginning. What I think is more important is, what do we teach them in terms of concepts, right? What is the intuition about what a quadratic algorithm is, or the intuition about what a crappy architecture is? That's the kind of things that we need to teach them. And I think this may be more important than getting that practical experience. Now, of course, we have University of Applied Sciences that take a different approach here, that value more the kind of practical experiences that are used. I don't know if that really is the right choice. I don't know how the situation was here in Austria. I remember 20 years ago, when we started to go from diploma study programs to bachelor's and master's study programs. Our industry friends told us, oh, you come up with all these theoretical things and students are too old, just give them a bachelor's of 4 years and then they will be good enough. It took 5 years. And they told us, please, can you teach them a bit more of the relevant concepts that you would need? So I'd be careful here. What we are seeing is that, at least in Munich, and in fact also in other places, we are seeing that industries suggest students that it's more important to have taken a job, like a research, like a HIVI, like a Werkstudent for some jobs, than to take classes. Some students buy that. I think these are capabilities that you learn sooner or later, because, and that's my last argument here, maybe, where do you stop, right? If you say, hey, I want to have a certain degree of professionalism and oversight over what software engineers are doing, where do you stop? Is it good enough to have 1 project? Do we need 2 projects? Do we need 3 projects? How many lines of code do they need to write? 10,000, 20,000, 50,000? So where do you stop? That doesn't mean that I think we should just do theoretical computer science and functional programming and formal verification, certainly not. But I think in terms of the education system that we are having, I wouldn't put too much emphasis on these parts because they learn that soon enough, in contrast to theoretical computer science.
Thank you. Thanks a lot. I'm a former software engineer a long time ago. Now, for 15 years, organizational consulting is my field. I very much like the differentiated analysis, and I want to ask from a HR perspective, what you say or what you state here won't replace professionals. So how professional will professionals need to be in terms of non-mediocre? And I would be curious if we take the whole volume of full-time equivalents of all software engineers in Europe, how would you see the statistics for the next 10 years of full-time equivalents, software developers? How do you think this curve will go for?
In terms of the number of software engineers that we'll have?
Not the number, the whole volume that we have now in the market. Is it going to shrink and then raise, or to shrink altogether, or is it going maybe to grow?
Here's my crystal ball once again, so I'm going to predict the future now. I think it will grow, and the reason is rather simple. Just because I may have a 3-fold increase of productivity, which we won't have, but just let's assume that, doesn't mean that I have 3 times less work. So in other words, if we have more workforce that can build that kind of software systems, then this is a huge potential for unlocking innovation that we may see here. And this is rather what I would see. So I see my former PhD students that have worked in companies that have founded their own companies. And they regularly tell me, hey, we now have a company that used to be 50 people. We could get rid of 20 or 30 of those, depending on the context. And these cases are happening, and that makes perfect sense. But then it turns out that these were extremely repetitive tasks. And now you could argue that the 20 people that are working here do many more things. And in fact, what they do is they triple their business in terms of what's going on. And if they want not just to triple it, but rather quadruple or quintuple it, then I think we would need more software engineers. In fact, I'm very concerned about the point that you're making. What I'm really afraid of is that parents read newspaper articles, and these newspaper articles say Gen AI will replace computer scientists. And then we do see that. In Scandinavia we see that, also in Germany in parts we see that. We see that in some American universities. We see a decline in the number of computer science / software engineering / computer engineering kind of students. And I think this really is problematic, because it simply is not true that we don't need that kind of expertise. Well, so here's my crystal ball.
Thank you for your talk. I just wanted to ask you, so your point was AI cannot simply replace the mid-level coder and engineer. What I'm asking is, there is kind of a contrast between coding and language kind of has similar characteristics compared to coding, as in it's very complex and there are different areas, different types of text, and the huge difference that we have for training LLMs for text and coding is we have millions and millions of books and resources to train our LLMs, but we don't have that much coding that we can feed to these AI models. And what I'm asking is, do you think over time, with more codes being generated and used to train these models, they can just like when you can write kind of any task with LLMs, LLMs can generate any kind of code?
I'm not sure I fully understand the question. So, I mean, what these LLMs are, they are completion engines, right? They just complete something that is being created, token after token after token after token. So that's...
But that's an accurate representation of knowledge, right?
Maybe it is. So the question, I guess, that you were asking is there a difference between natural language and code? And of course, there's more natural language on the internet than code, but there's huge bodies of code, open source software repositories, which is exactly the code that is being used for training these models. So I'm not sure I fully understand your question.
What I'm asking is, in area of text is very, very hard to understand, and the knowledge representation is very hard and complex in different areas, and LLMs got that pretty much.
Taste, you mean
for
taste?
Text, yes, for text knowledge.
Oh, for text, yeah?
Text, but yes. What I'm asking is, how can you say that they won't understand the code as good or as well as a mid-level engineer?
I actually didn't say that. I never talked about understanding, because these systems also don't understand anything. My point was, somebody needs to say what the LLM is supposed to do. That's what I meant by the intent. And we need somebody who is capable of phrasing that intent. And the capability of phrasing that intent requires understanding of software technology and also of the application or business domain. Sorry, maybe we can take that offline.
Okay. Perfect.
Is that what you meant?
I'm a student, so my questions can be dived a bit. So the industry is more like money driven, right?
What?
It's software engineering industry is money driven. It's money driven. The top gives the money and distributed between the jobs. So where you put the line that most of the jobs in the industry, like the money goes, because like professional, you have some stats to like back your thinking that it's when you say intent, so 20% of the money goes to the intent and 80% of the money goes to people who are doing the business roadmap. So my question was like, do you have some stats to back it up?
No, I don't. So I also didn't put any numbers here because I simply don't know them. I would assume that most software is written probably by these two classes of people here.
So for me, how I see generative AI, it's like the automation of the industry, human how we write code. So it was like industrial revolution, we had, so we were having like, if we are making furnitures, back then we had like 2,000 people making 2,000 of different kind of furnitures. So now the output, the item made 80% of them. So it's a service-based industry, right? The software. So we're making money by So the output goes to people. So now people who used to think and goes to 2,000 different people, and their mindset was a high quality output they want for money. But now it's reached back to a low quality furniture from IP. You understand my point?
Yeah. So I think I'm not sure I buy that argument, right? There always is a trade-off, of course, between quality and money. Usually, you spend more money, you get better quality.
So that's the point I was making, that most money is going towards the low quality. So we automated content how we make. We used to make good movies back then. I used to watch one movie in a week. It was a really good made, human-made movie. So now the content is more automated by the software. So I watch reels, a lot of reels, and these factors that I'm getting, it's the service I'm having and I'm paid for. I'm not paying for that good movie for after a week thing. So after software develops is generated by Generative, the quality is going down, but that's how people interpret it.
Power plant control software, I think people will still care about quality.
Yeah, that's why I asked you the first question.
I think that maybe a larger point, I think Professor Pretschner will be there after the talk. Maybe you can take it offline?
Can I go back to the first question again?
Sure, make it short. Okay.
Yeah. So the first question again, the industry are talking about nuclear medicine, they won't go for the software engineers who have low quality very organized, they go for the high professional. So back to again, if you have some stats that to present that there's low quality industry which has more money, are they going for the general people or people like this?
As I said, I don't have these numbers, I don't know. Also, let's also be clear, right? The state of affairs today in industry is not that all tasks or many tasks are taken over by Gen AI. The companies that I'm working with, they are experimenting. And everybody is using Copilot, and everybody is playing with Claude and the related tools that come with that. But at a large scale, people don't use that yet, I think. Yeah. There's one more question in the back there.
Okay, so there are a few more questions. Question to our dean: how much time do we have for questions? How much time do we want to have? We have time? Fantastic. All right. So we have one here, and then we have a few over there.
Thank you for your presentation. And my question is mostly related to AI rather than to software engineering. I am a master's student, and in your presentation, you mentioned that there is a high probability that junior engineers won't be much needed in the industry. AI does the job.
Sorry, I have difficulties understanding you. Say again.
Is it clear?
It's just the quality of sound is difficult for me because of echoes. Go ahead.
Okay. In your presentation, you said that junior engineers will be most likely be replaced by Gen AI, and professional engineers will be needed in the industry. And my question to you is, as a student who is new in the field of AI, learning AI, and wishing to be a professional, what should be the learning approach? Should we focus on the details of, we are using libraries, packages already available, right? And should we focus on understanding all the underlying code, mathematics, and maybe the training of LLMs, transformer architecture, RLHF, everything? Or should we focus on implementation part, connecting things to make a product? What should be the learning approach so that I do not fall in the category of junior for a long time and be a professional real soon?
Okay, so again, the sound quality is problematic here in the front row. If I understand correctly, your question is, as a student, I assume, of computer science, the question is, should you rather focus on implementing systems and the capabilities that come with that, or on the foundations of machine learning?
Exactly. is it necessary to understand everything that is inside the black box, or the overall architecture should be the major focus?
So I have a very simple answer to that: follow your heart. Of course, you need to have a working understanding of both areas if you want to excel in that field, right? You can't do everything at the same time, so my suggestion is do what tickles your fancy. Some people are more into the software engineering part, some people are more into the theoretical ideas behind machine learning. We have a debate at my university about compulsory machine learning classes in the bachelor's program. And some people say we absolutely need that, and some people say, well, we don't really need that, also at the level of the master's programs. And I'm not sure we absolutely need that kind of compulsory classes. I'm not sure we need the theoretical foundations drilled into our students, because I'm not sure that most of them will need that. Just very few will develop new machine learning models or whatever. I think what is more important is to understand what are the pipelines, what is data cleaning, what is bias, that kind of thing. So the practical applications, that is something that I personally would see here as more important. But be very careful with that kind of response, because I'm giving you my response, Gerti is giving you a totally different response, and Nisrit is giving you a third response. So don't take that for granted. I think there won't be too many people that will work on improving machine learning algorithms. There will be some, and here at your university, there's fabulous people who do that. That's perfectly fine. I think for the majority of students that graduate, the job will rather be in building applications. Difficult question.
I have a question that's probably related to the one that was just asked. Regarding your experience as a teacher, now with Gen AI readily available, should we teach new students, new software engineers to use them from the beginning? Or do you see still value in them first learning how to write software, let's say, unassisted by themselves?
I'm giving you my answer. And again, Jürgen will have a totally different answer, and Nisrit will have again his third answer, right? So there's no claim for truth of what I'm saying. I can tell you what I do in my introductory classes. I'm teaching Introduction to Programming or Introduction to Informatics, and that's a bit of algorithmic stuff with Java, essentially. We teach them how to program in Java. And in that introductory class, for the last 2 or 3 years, I have thought about potentially changing that class, and I didn't. And the reason is the following. I think, if you remember the figure that I've shown you, where we see that relationship between creating and verifying, we need to enable students to verify what has been done. And that, of course, requires a bunch of different things. Among other things, it requires experience, which, as we have discussed before, probably can only come later on. But in order to at least appreciate a piece of code, I think you need to fundamentally understand what coding is. And in fact, that is not the case for all activities, right? All of us can know how to play soccer, right? Everybody here can sit in front of a TV set and say, no, I would have done that, and that trainer should go home, and so on, right? It's also cooking, right? Sometimes we go to fancy restaurants, and we can maybe appreciate the quality of the food without being able of doing these things ourselves. But I think for an engineer, specifically for a software engineer, it's absolutely mandatory to have coded at least some in order to understand what is going on with the code. For instance, if you take polymorph, are you from the field? Are you from software engineering? Yeah? Do you know polymorphism? Polymorphism is really extremely complicated, specifically if you go beyond the simple introductory examples. You must have done some polymorphism in your own coding experience before you can really appreciate that. And then the question is, once again, it's always a matter of trade-offs. It's not that I wouldn't want them to come up with LLM-based aids or assistants, and I wouldn't want to teach them that kind of things. It's just that I think, hey, the other things are important enough. They should learn those first. So I haven't changed anything. I was thinking about teaching a class on AI-based software engineering. And I was really excited about that idea, and I have come up with a concept. And then I talked to the members of my group who, let's be honest, would have had to take some of that load on them. And maybe because they didn't want to do that, or maybe for other reasons, they pointed me at one observation, and that is, if we came up with these tools and techniques today, we would probably have to change everything 12 months from now. So there's also a practical, and that's essentially mean that in the end I didn't come up with such a class. But that's for laziness, because I knew if I do it once, it's going to be a huge body of work. I will have to redo it next year, and I'm not sure I can do that. Last point is, these children, they use these systems anyway, right? It's like teaching children in school how to use an iPad. I mean, how ridiculous is that? Yeah.
My question is, have you already observed that how code looks like has changed with the use of generative AI and all these coding tools, so that maybe even the solution completely changed because now people use these Gen AI tools? And maybe then thinking even further, does the quality of these Gen AI tools change because they are retrained with the code they have generated by themselves? And this is like an endless feedback loop.
Excellent question, very, very, very interesting. So I can't answer the second question because this is an extension of the first question over time, and I don't have that experience. I can answer the first question, not with respect to the code that I myself have seen, but by talking to many companies in the Munich ecosystem, right? Like you guys meet, we also meet, and we chat about that kind of things. And there's one statement that I have often heard over the last couple of months, and that is, so usually it's organized in a way that juniors provide the code that is then reviewed by seniors. That's usually the idea. And the seniors complain that the code is crappy because it has been generated by AI. It doesn't really see the right abstractions. It does things in an awkward way. And this is not a scientific argument. This is not backed by any empirical studies. But the gut feel of these seniors is the quality is worse. That may also be, of course, because they are old people who think, oh no, these new technologies, so there's a certain risk of bias, of course. But in contrast, I have never heard a senior person who has told me it's fabulous, the code that I'm getting by the LLM. That's something I've never heard.
Any questions? Okay.
You're running Fortis, this kind of applied software research institute. Which kind of tools, or how many tools are you using and are used in Fortis to develop software?
Yes.
And do you see a productivity gain or a change in quality, for example?
Yeah. So are you asking for precise tools that people are using? I can't tell you because we use all of them, right? What we do have, we have one department, Center for Code Excellence, that is concerned with understanding what the impact of these tools on coding is. And we collect that, and they experiment with all these different tools, with all the different LLMs, and they then come up with recommendations in certain situations to use this or that. And again, I can't answer that question because this is context specific. It's not that, hey, use Claude something for all tasks. It really depends on what you want to do. Claude usually is extremely good. That's what we are seeing. In most cases, that's better than all others.
My question is, I see that you take your point about how LLM can replace is based on how LLM it is now, like how it is trained to only provide the response based on what the prompt is. And then the contrast to what we train to be like open-ended response, like if we are trying to imitate ourselves as an agent that helping the software engineer, then we need to deal with a scope of a project, a software project, and then every time response, we are not limited to providing something that is complete. So probably when we implement the code, we not implement the whole code from the procedure of a body, but we only say probably a stub function, and this will be related to this and that. Is it because how LLM trains right now is not appropriate for the code? What if in the future that LLMs are specifically trained to this kind of open-ended question? So it's not answering the complete answer, but it can follow up what's the context it's going on. So it's like a more like a current approach, not like a autoregressive manner, but in the diffusion manner.
Yeah. Good question. So I think my same argument applies to that situation as well. And again, in fact, what we are seeing today is we have these iterations, and whether or not the LLM asks back, hey, did you mean this or did you mean that, doesn't really matter for the treaties that I have tried to present here. So, if I understand correctly, what you're asking is aren't we going to see a way that software is developed that is more conversational, in terms of questions being asked forth and back and somehow leading to some place? And the answer is, yes, we are going to see that. I'm convinced of that. But if you have a dialogue between two parties, then one of the parties is the software engineer. And this is exactly the point that I'm making. Yes, we will see that, and we will increase the productivity, most likely, of software engineers. But in a dialogue, by definition, you need a second party, which would be the human. And we can't replace that by another LLM because of the intent argument that I've tried to convey here.
Can I take a follow-up question?
Sure. Jürgen is the boss, so.
So in this case, like in the future, we are increasing the capacity of a software engineer, as previously we are limited to do as a solo developer. In the future, with the advance of the software engineering assisting agent, we can expect more from one developer to do more. And then we have like smaller software engineering teams. And what's...
That's the point that I've tried to make before, right?
Yes.
Just because we have increased the productivity doesn't mean that the overall work stays the same or becomes less. I could imagine that if we increase the productivity by 20%, then we can also increase the amount of things that we want to do by 20%, which means that the net workforce is the same.
Okay, that's fair. Thank you.
So I've been told by the boss that we have one last question, okay? In that case, I'll allow myself to ask the last question. So I think the discourse in general, and also so far in this talk, has been pretty labor market specific in terms of value. I wonder, given your perspective on the shift of creation to more verification, are we rationalizing away the fun parts of software engineering and leaving the fun part to the machine and the not so fun part, the verification, the review, to the human? What's your perspective on this?
I think yes, that's what's going to happen, right? And in fact, maybe that's a certain irony. You can see the agile development as an empowerment of software engineers, right? This is exactly what was happening there, among other things. It was a cultural revolution that was taking place, because software engineers said, hey, we can decide ourselves what needs to be developed next. We don't need a manager for that. So yes, I can imagine that things become less happy. As you know, my field of expertise really is software testing. And I realize that software testing isn't exactly something that most people think is a very creative kind of job. I, of course, see that differently. But testers don't really want to be testers, or software engineers rarely want to be testers. Why? Because creating stuff somehow is, or seems to be, more stuff than testing that. But the question is that a good argument, right? Should we say, hey, we get rid of these productivity gains just because some nerds like you and I want to have more fun? That's certainly not an argument that I would make.
I don't think that's the argument I would make, just as a closing point here. The argument I would make is, should we rediscover how we approach the verification part to make it more fun?
Potentially. Yes, we should. But I guess the verification part really is the more problematic part, because in terms of verification, you really need to think about, hey, what is going on here? I've never come up with that thought. But when we develop stuff, we do that in an iterative way, right? We develop a bit, we do a bit more, and we see how things work. In fact, in terms of the verification, you don't have that activity. It's not that you think, oh, perfect, I'm going to create my test cases in that iterative manner. That's not what's going to happen. Rather, you need to think about what the system is doing, and then you are forced to think about, hey, for this input, I would expect that output, and this is the set of inputs that I'm interested in. And maybe this is exactly what testers don't really enjoy, or what most software engineers don't really. I need to think about that.
Okay, fantastic. Thank you very much. So let's thank Professor Pretschner together.
Thank you.
And I also want to give the word to our dean, Professor Kapper.
Just as a last word, as it was really great, Alex, to have you here. And when you have mentioned digital humanism quite some time on your slide, and you, in fact, you should all know that Alexander Pretschner and his team, they also developed an own software development kind of process, taking ethical considerations into concern, like this EDAPS, ethical deliberation of agile process software, of agile software development. Everything great. So if you want to read more about this, there are books like Introduction to Digital Humanism I have here, and so on. But what I really wanted to say, I want to thank you. And since it's soon Christmas, there's a little present which I hope you will enjoy. Thank you very much.
Thanks very much. Thank you.